Hello everybody. I am Jeffin Johnson, Assistant Professor of Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. So in this session, we will be discussing about the different atom models, atomic interaction, as well as atomic bonding. So if you look into the history of atom models, we can see starting from 1803, John Dalton developed a solid sphere model. Then 1904, J.J. Thomson made a PLUM pudding model, a nuclear model by Ernest Rutherford in 1911, planetary model by Niels Bohr 1913, Erwin Strontinger, the quantum model in 1926. So if you look into this model separately, the first one is done by John Dalton. So Dalton drew upon an ancient Greek idea of atoms. That is, the word atom comes from the Greek atomos. The meaning is indivisible. So his theory stated that atoms are indivisible. Those of a given element are identical, and compounds are combinations of different types of atoms. So John Dalton, there was no nucleus. He was not even saying there is a nucleus, a positively charged, negatively charged. So he was given a simple solid sphere model. In the second model, there is a PLUM pudding model that is discovered by J.J. Thomson, 1904. He discovered electrons, which he called corpuscles at that point of time, in atoms in 1897, for which he won a Nobel Prize. He subsequently produced the PLUM pudding model of the atom, shows the atom is composed of electrons scattered throughout a spherical cloud of positive charge. So he understood there is a positive charge, there is a negative charge, and that will be mixed, that will be surrounded, that positive charge will be surrounded with the negatively charged particles. Third model, you can see a nuclear model done by Ernest Rutherford in 1911. So he fired some positively charged alpha particles at a thin sheet of gold foil. So most passed through with little deflection, but some deflected at larger angles. So this was only possible if the atom was mostly empty space, with the positive charge concentrated in the center of the nucleus. So he understood there is a positive nucleus at the center point of the atom, and there is a wide vacant spaces available. So that is the reason why some deflected smaller angles, some deflected larger angles. So there are several. So he made some orbits out of the positive nucleus. That's simply termed as nuclear model. Then there is a planetary model. That's done by Niels Bohr. It was widely accepted at the point of discovery. 1913, modified Rutherford's model of the atom by stating that electrons moved around the nucleus in orbits of fixed sizes and energies. Electron energy in this model was quantized. Electrons could not occupy values of energy between the fixed energy levels. So we can see there is a positive nucleus present there with protons and neutrons. The electrons will be moving around the positive nucleus in fixed orbits, that is discrete orbits. But this model has a limitation. It doesn't obey the Heisenberg's uncertainty principle. So later this model was modified. It's a quantum model. So Erwin Strontinger in 1926 stated that the electrons do not move in set paths around the nucleus, but in waves. So it is impossible to know the exact location of the electrons. So instead we have clouds of probability that called orbitals, in which we are more likely to find an electron. There is a possibility, there is a probability that we could find electron there, rather than simply saying that it will be moving in the fixed orbit. So this was a model nowadays being followed. Stations for each and every model. If you consider the solid sphere model, it recognized electrons as components of atoms. It's not the pure atoms, it's only about protons and neutrons, not like that. The electrons are also components of atoms. But there was no nucleus, it didn't explain about those things. Then second model, PLUM pudding model, this model realized positive charge was localized in the nucleus of an atom. But still didn't explain about why electrons remain in orbit around the nucleus. There was no orbit. He was just making a point that the electrons would be moving around, or it will be like a positive, it will be like a pudding type of model he made. There was no fixed path likewise, sort of thing. The third model by Rutherford, he recognized electrons as components of atoms, but here also there was no nucleus. He didn't explain that thing also. But Niels Bohr realized there is a positive charge was there, it's localized in the nucleus of atom. But still here, he didn't say why these electrons remain in the orbit around the nucleus. Because this model will be applicable to elements having lesser electrons. If you consider atomic numbers, high atomic number elements, it will be difficult to study this model on the basis of this model. Then Erwin Staudinger proposed stable electron orbits, explained the emission spectra of some elements. But moving electrons should emit energy and collapse into the nucleus model did not work well for heavier atoms. Here also, heavier atoms, it will not work well. So these were the findings and the limitations of the different models that we explained. So atomic model, if you consider, there are two types, the Bohr model and wave mechanical model. So Bohr model, we can see the discrete orbits. Bohr atomic model proposed that electrons orbit around the nucleus in discrete orbitals, thus K, L, M, N, likewise, which are having specific energy levels as well. Positions of electrons in the orbits, it's well defined. An electron can change orbit by emitting or absorbing the quanta of energy. So suppose we can see, suppose from the second shell, the electron moves to the higher energy level by absorbing energy, or absorbing photon. So now the electron is at a higher energy level, it's not stable. So electrons will be always having a tendency to be in stable state. So it will emit the photon, so thereby it will be reaching back to its stable normal state of energy level. This is a simple Bohr model been explained. So there are some limitations as well. We could not explain the spectra of atoms containing more than one electron. So it will be clearly giving you the idea of a hydrogen atom. Rather than heavier atoms, it will be difficult for this model to explain. And also it violates the Heisenberg's uncertainty principle, since Bohr's model predicts both position and momentum at the same time. So it is not actually possible by Heisenberg's principle. Then a new model is the wave mechanical model. In this model, the limitations of Bohr model was resolved, and electrons are considered to behave both wave-like and particle-like. We can only find a region where the probability of finding electron will be there, rather than a discrete point where the electrons will be exactly located. It could not be possible, but we can see that the Bohr radius that already calculated by an equation. So that will be the region where we can have a probability. So there is significance also. The Bohr radius also have a particular significance in this model as well. Electrons are no longer treated as a particle moving in discrete orbitals. Position of an electron is described by a probability distribution. So there is a probability to find an electron. So there is a cloud-like region that will be present. So here we can see instead of a solid circle, we are having a cloud-like feature where we can see there is a possibility of electron there. And there is, if you look at the graph, there is a probability that the distance from the nucleus. If the distance from the nucleus is 0, probability is 0. Then if we increase, the distance is moving away from the nucleus, the distance increases gradually, so we can see there is a probability. So that probability region is same as, and its maximum at Bohr's radius. So even if the Bohr's model is not giving you an idea whether that electron is moving in the orbits, how is it possible? But still we can see the Bohr's radius could be easily used to find out a probability region where we can find the electrons. So this is the probability distribution of electrons. So this is the wave model. So we can see, if we consider a fixed circular orbit, the mass of the electron m, then the velocity at which it is moving, r is the Bohr radius. So this is the equation to find out the Bohr radius, 4 pi epsilon 0 h dash square divided by me square, where m is the mass of the electron, e is the electron charge, and h dash is given by h by 2k, where h is the Planck's constant. You can see from the nucleus, from the graph itself, if the distance from the nucleus increases, there is a point at which we can find out the probability, find out a region where possibility of electron is more. Then quantum numbers. So consider 4 parameters or numbers called quantum numbers are needed to describe the distribution and position of electrons in an atom. So first 3 of them, N, L, M, describe the size, shape, and spatial orientation of the probability, density, distribution of electrons. So if we consider the principal quantum number N, describes electron shells. So we can see 1, 2, 3, 4, that is different energy levels, which are normally labeled as K, L, M, N, where K is having lower energy. Value of N determines the size or distance of the shells from the nucleus. So nth shell means it is very far away from nucleus. And there is an equation to find out the number of electrons in a shell, that is given by 2 into n square. So if we are considering the first shell, so 2 into 1 square, that is equal to 2. And second shell is normally labeled as L. N equal to 2, so 2 into 2 square, that is equal to 8. So likewise we can find out the number of electrons at a particular shell. Then electronic configuration. You can see the configuration means a manner in which electron states are occupied in a given atom. So there are several number of shells available, and this is the maximum number of electrons as per the equation. So first shell is 2, then 8, then 18, then 32. And also we can have SPDF like sort of arrangement, where this is the way how the electrons will be oriented, the electrons will be configured. So this all shows a stable kind of a configuration. There are 2 principles also how to fill the shells, the Aufbau principle and Madelung principle. So that principles give you which is the shell that has to be written in the configuration based on the energy level. For example, after 3p it's not 3d, the 4s having lower energy comparing with the 3d. So we have to write 4s before 3d. So such kind of a principle is available in order to properly write the electronic configuration. So if we consider 2 stable and unstable type examples, sodium, if you consider, you can see the third shell only 1 electron, but up to 2p shell we can see it's a 2p energy level, you can see it's almost stable. So this electron, if it relieve this particular electron, then we can say sodium as a stable element. So sodium always have a tendency to donate, so that is the reason why it is one of the electropositivity element. But on the other hand, if a stable case can consider noble gas is one of the argon, one of the noble gases argon, we can see up to 3p6 almost filled with electrons and it is stable. So that's the reason why the noble gases or inert gases will not take place in reactions, because they are already stable, they don't want to be unstable. But sodium, if you consider a chlorine atom, so that will be combined together to get sodium chloride, because the chlorine needs 1 electron and sodium has to donate 1 electron. So both will be combined and become stable compound. So if you consider atomic interaction between the 2 atoms on the basis of the poles, you can see if you consider 2 atoms that are separated by distance, nucleus is having positive charge, electrons are having negative charge. So when 2 atoms are together or separated by only a small distance, and it will be attracted, the nucleus, positive charged nucleus will be attracted by the negatively charged electrons in the second atom, similarly, and it will be attracted, and at a particular point what happens is the positive nucleus of the one atom and the positive nucleus of the second atom will start repel. So there is a repulsive force as well. So whenever the distance between the 2 atoms gradually reduces, and also that same is applicable to the negatively charged electrons as well. So from the graph we can see this is a blue line is given, blue color is given to the attractive force, Green is given for the repulsive force. And there is a net force, that is sum of attractive force and repulsive force. And at a particular point, the attractive force and repulsive force coincide together. And that means there is no more interaction. There is a RO, that is interatomic separation. That is a stable kind of separation. The reason why the force that is given in the x-axis is exactly 0. That means there is no net force acting. An optimum attractive force and optimum repulsive force will be there. So the net force will be 0 at a point where considered as R0, that is interatomic separation is R0, then the net force will be 0. So if you consider that force in terms of energy, that is potential energy, attractive energy as well as repulsive energy, here also if you consider that same point R0 that has been indicated in the second graph, that is the equilibrium separation. Equilibrium separation is stable separation between two atoms. And above that graph, there is repulsive energy will be there more for the atoms. If again that atoms get separated, atom gets closer together, so that there is a large possibility of repulsive energy that has been generated between the positive nucleus as well as the negative electrons. But in the bottom side of the graph, if you consider the two atoms and the distance is more, then the atoms will be having a tendency to join together because of the attraction of negatively charged electrons with the positive charged nucleus of the another atom. So there will be an equilibrium point at which both the atoms will be separated by a distance that is R0, the interatomic distance, that is considered to be the equilibrium distance. And if you extend that point and draw a vertical line, we can see the net energy line, net energy graph plot, where we can find a point that is minimum energy. So that means if we consider net force point, at that particular point there will be minimum potential energy of that atoms. So that simply means there won't be taking place in any kind of activity, since the energy is minimum, and they will be in stable equilibrium condition. Atomic interaction. Why this atomic interaction happens? Attractive force is due to electrostatic attraction between the electrons and nucleus. Repulsive force is due to when separation is less than equilibrium, repulsion takes place between nuclei of interacting atoms or electrons of interacting atoms. So the inference is at the equilibrium separation, net force is 0 and potential energy will be minimum. So that is the reason why, if you consider that energy, the previous, that is a graph E0, that is the bond energy, that clearly interprets whether the material is having higher melting point or higher elastic modulus, like sort of properties. So if you consider solid, it is closely compacted together. The interatomic distance is much more stable. So it will be that because of a high bonding, stronger bonding, it will be difficult to separate the atomic particles. So that is the reason why the melting point of such metals, such solid bodies are higher comparing with the others. If you consider liquid, if you melt the material, it will be in a liquid form. So the atoms can move accordingly, more free to move. So such sort of thing, it will be atomic bonding will be lesser. So higher bond energy means higher melting point as well as higher elastic modulus. So the three types of primary interactive atomic bonds are there: ionic bonding, covalent bonding, as well as metallic bonding, which is considered to be stronger bonds. Then secondary bonds like van der Waals forces as well as hydrogen bonds, which are much weaker bonds. If you take an example of graphite structure, we are having the covalent bonds between the carbon, but because of the layers, different layers available with the graphite, the layers will be having van der Waals forces, much weaker forces comparing with the primary interatomic bonds. So that is the reason why it is considered to be softer material. So if you look into detail about its primary atomic interatomic bond, first one is ionic bond, that is between metallic and non-metallic atoms. So metallic atom give valence electrons to the non-metallic atom. So take an example, sodium atom. You can see one electron is considered to be an excess, which makes that unstable. But if you consider chlorine atom, it requires one atom third shell to become stable. So by donating, that is electropositive positivity atom, the sodium atom will be donating the electron. At the same time, the electronegativity chlorine atom will be accepting the electron. So thereby it will be forming ions. That is much stable ions. So there will be Coulombic attraction between two oppositively charged ions. So we can see there is an electron transfer from the sodium to the chlorine. Type of bond is covalent bond. Here also it is a stronger bond, but there is a sharing of electrons rather than permanent transfer. It is simply sharing of valence electrons to get a stable configuration. For example, methane, if you consider CH4. In the case of carbon atoms, only 4 electrons at the outer shell. So hydrogen atom, if you consider only one electron. So it can be combined 4 times with the carbon atom. So thereby we will get a CH4, which is a stronger bond. So it is formed between atoms of similar electronegativity. But in the case of ionic bonds, one is electropositivity atom, the another one will be electronegativity, having electronegativity. So we can see examples like diamond, silicon, germanium also have covalent bonds. So diamond is one of the hardest material. We can see covalent bonds to be stronger, providing the atom with the stronger bonds. The type is metallic bond. That is experienced in metals, mainly metals. So atoms have fixed position in the crystal. So here the valence electrons are free to move as free electrons, forming an electron cloud, and there will be positive cores, ion cores as well. So metallic bond arises out of the Coulombic attraction between these two oppositively charged species, the electron cloud and the ion cores. So due to free electrons, because the free electrons, very high conductivity is possible in the case of metals. So if you look into the secondary bonding, that is van der Waals bonding, that is much more weaker. So weaker in comparison to primary bonds, typically 10 kilojoules per mole. It's only the bond strength. It arises due to atoms molecule dipoles, which form due to separation of positive and negative species of an atom or molecule. Bonding results from Coulombic attraction between positive dipole and negative of one atom to the negative positive of adjacent atoms. So in graphite bonding, we can see between the layers there is van der Waals force of attraction, which is much weaker comparing to the primary interatomic bond. So this is the figure that showing the graphite structure. The carbon will be having covalent bond, but in the case separate layers are bonded with the help of van der Waals bonding. So that is the reason why it's considered to be one of the softer material. So we can see the positive and negative dipoles that will be attracted together, and it's much weaker in terms of bond strength. Then another type of bonding is hydrogen bonding. So this type of bonding is found in molecules that have hydrogen as one of the constituent. Electrostatic interaction between hydrogen and another atom of high electronegativity. You can see H2O, water molecule, is a good example of this type of bonding, that is between hydrogen of one molecule with oxygen of another molecule. Of the different bonds that we studied, primary interatomic bonding as well as secondary bonding. You can say ionic and covalent bonds are much stronger because the bond strength is up to 1000 kilojoules per mole. So those materials having ionic covalent bond, having higher melting point as well as strength, hardness, mechanical properties will be superior for those materials having ionic and covalent bonds. Lower conductivity, behavior is brittle. Example like ceramics, diamond, etc. possess this sort of bonding. The next is metallic bonds. It's a moderate bond strength is there. If you consider mercury, then tungsten, then 68 kilojoules per mole as well as 849 kilojoules per mole. Even if we can see some sort of tungsten material, it's also having a better amount of bond strength. That is the reason why it possesses higher melting point. So bond strength is there, melting point is higher, strength, hardness, etc. increases with the atomic number. So in the case of metallic bonds, there is a dependence with the atomic number. More the value of atomic number, more melting point as well as the properties. Behavior is generally ductile. Then secondary bonds, if you come across van der Waals, the bond strength is weak. You can see argon and chlorine molecules 7.7 kilojoules per mole and 31 kilojoules per mole. So bond strength is very less compared with the earlier bonds. Then hydrogen bond, it's a weak bond strength. You can see the compounds comprising hydrogen as the primary constituent gets 35. Ammonia 35 kilojoules per mole, water 51 kilojoules per mole. So this is the summary of the bond strength of different bonds that we studied for atomic interaction. Okay.